Hi guys, we have chapter 34, number 47 here, where we're given a square loop shown as in a figure, and it's moving into a B field with zero point 0.8 Tesla magnetic field, and it's moving in with a constant velocity of 10 meters per second, and it's saying this loop, this square loop here, has a resistance of 0.1 ohms, and it enters the field. This is our B field here. It enters at time equals 0. Just that very first tip is going to be entering at time equals 0. And it asks us to find the induced current in the loop as a function of time and give our answer as a graph. And then part B, it's going to ask what is our max current and the position of the loop when the current is maximum. So we'll start by determining the induced current in the loop. So we know the loop here is entering a B field. The area is slowly going to get swarmed more and more of it as it moves in with this B field. So we know we're going to have a changing area with respect to time. And so first, we're going to need to know what our area is as it enters. Later in the question, it's going to ask for our maximum. That's when it's halfway into the B field. Current's going to be increasing constantly. So when it hits this maximum, then the current will be at its max at halfway, and as soon as it gets more than halfway, it's going to start going down again. So because of that, it's going to be halfway in. We're going to do two triangles here. It's going to be half this square loop, and we're going to need to determine the area. The area is going to be 1/2 base times height for each triangle, but because there's two of them, the 2 and the 1/2 cancel out, and we're just left with our area to be x squared. Now, as a function of time, it's the velocity times the time gives us our position of x. So velocity times time quantity squared is going to be our area in terms of t. We're going to need to take the derivative of this v squared t squared with respect to t, and that gives us 2v squared t. Now the reason we do that is because when we're finding the induced current, we're using Faraday's law here, and because we have changing area with respect to time, that's our change in flux, then we're going to need that to plug into this equation. Now, when we plug that into our equation, we are going to solve through for epsilon, and we get that epsilon is 160 T. To determine the current, we're going to plug that into I equals V over R, and 160 T, the epsilon that we just solved for, divided by the resistance given in the problem at the beginning, is going to tell us our current, our induced current here, is going to be 1600 times T. Now that is a constant current that is increasing until it reaches this halfway point, and as soon as it goes beyond that halfway point for that loop, then our induced current will start decreasing. So with this graph, the graph that part A would like us to answer with, we know that it's increasing with a constant speed, or at a constant rate, current in terms of amps, time in terms of milliseconds. It's constantly increasing, and it hits its max point when it's halfway into the B field, and then it starts to decrease. Now, we don't really have values for these times yet because that's what part B is going to give us. Part B wants to know what this maximum is right here, what that max is, and at what time does that occur. And this is going to be from 0 seconds right here until 0.02 seconds, I apologize, is what the book would ask for. So I'm going to do 20 milliseconds right there. And this is going to be 0 amps right here, and we're going to find out what the max current is and the time at which that occurs. So in order to do that, we know it needs to be halfway. So in order for it to be halfway, we're going to have the position be 10 divided by root 2, and that's going to represent our position when it's halfway. Now position, again, much like earlier, is velocity times time. So 10 over root 2 is going to equal velocity times time. Our velocity as we determined earlier, or as was given to us actually, velocity is 10 meters per second. So then we solve and we get time is equal to 7.1 meters per second. And, milliseconds, I apologize. The 10 here is 10 centimeters divided by root 2, so I'll make note of that. You guys can do the conversion into meters. And then you solve and you get time is 7.1 milliseconds. Now we can plug that into this earlier equation that we solved for. 1600 times 7.1 times 10 to the negative third will give you your current max, and that ends up being 11 amps. So now on this graph, if you feel like it, you can put that your max current occurs at 7.1 milliseconds, and it reaches a height of 11 amps. And with that, we have solved chapter 34, number 47. Thank you.